waves. So first of all, what kind of waves are sound waves? Sound waves are longitudinal mechanical waves. Okay, they are longitudinal. Remember, the electromagnetic waves were transverse waves, right? Sound waves, on the other hand, they are longitudinal waves. Okay, what does this mean? That means comprising vibration in matter where the vibration are parallel to the direction of the wave motion. For the electromagnetic waves, they were perpendicular. Okay, they were perpendicular, but for the sound waves, they are parallel to the direction of the wave motion. Sound waves, they are mechanical waves. Okay, what does this mean? That means they require a material or medium to travel through. Okay, they cannot travel through the air or through the vacuum. They are mechanical waves. Okay, so they travel through air, but again, it needs like gas molecules. It needs gas molecules. For example, when I talk right now, you can hear me, right? This is because of the molecules around. They are carrying my sound and bringing to the computer speaker, and then you can hear me. On the other hand, think about it. Like when a person try to talk to you in a long distance, sometimes you cannot hear them, right? That is because those molecules do not have enough energy to carry sound waves to your ear. Okay, that's why the sound waves need medium or material to travel through. Okay, they cannot travel through the vacuum. This is important part of the longitudinal waves. Okay, longitudinal waves. Remember the difference between longitudinal and transverse waves. One of them needs material to travel through. The other one, the transverse waves, do not need any material to travel through. Okay, they can travel through the vacuum. So sound waves are a series of compression and rarefication. Rarefication means, like, remember rarefication and compression. Yeah, these two terms in the previous lesson we learned about them. Compression, like when you compress the waves. Okay, when you compress the waves, this is going to be a sound waves. So how hearing happens? Hearing, the important part of the sound waves. So remember, our eardrums and members in the ear that vibrate when a sound wave enters the ear canal. Okay, we have for each person, like for young people especially, there is an audible range, which is between 20 hertz to 20,000 hertz. Last time I checked, for example, I checked my hearing, it was around 15,000 hertz. What does this mean? It means when you get like older and older, your hearing is going to be less than when you are young. Right now, you guys probably are hearing like around 20,000 hertz, your frequency. So we call this a range, audible range. Okay, audible range. So this varies from person to person, and factors such as age and exposure to loud music dramatically change this range. If you listen music too much, especially on the loud sound, you are going to have problem in your ears. So the frequency of over here is going to decrease in time when you listen too much music. Okay, so you have to be careful when you listen music. You have to arrange the sound properly. The volume must be proper. Okay, if you listen music in a high volume, this is going to affect your ears negatively, and you're going to lose your hearing. Okay, so what about the speed of sound? So the speed of sound in the air is around 340 meter per second. So this is around 900,000 times slower than light. Remember that the light, the speed of light is 300,000 kilometer per hour. Okay, 300,000 kilometer per hour. And when you come to the here, it is 340 meter per second, or we can say like the speed of light is 300 million meter per second. When you compare it, so it is 900,000 times slower than the light. What is the reason of this? The reason is the sound waves, they need the required material, but the in the air, on the other hand, the light does not require any material to travel through. Okay, so sound travels at a different speeds through different materials. They best travel in the solid materials. Okay, solid material, because their molecules are close to each other, and they can carry sound waves properly. It happens the best in solid, then liquid, then gas. Okay, the sound travel like that. That means when the material is denser, the sound the speed of the sound will be faster. Okay, one material is denser, the speed of sound will be denser. So when sound waves travel through gases, things are a little more complex due to the motion of the particles. Remember, so the density of the gas has an effect, but if two gases were at the same temperature, then sound would travel faster through the denser gas. Okay, if they are in the same temperature, but one of them is denser than the other one. For example, let's say there is oxygen and carbon. If carbon is like denser than the oxygen, it is going to travel. The sound is going to travel faster in carbon than the oxygen. Okay, at the same temperature. But the temperature of the gas has a significant effect. Okay, temperature of the gas increase the speed of the sound. Okay, why? Because remember, when you hit something, the material will gain kinetic energy. When material get kinetic energy, it is going to get faster. Remember, gaining kinetic energy means getting faster. So whenever a gas has high temperature, you're gonna say that the speed of the sound here is going to be faster. So we are gonna use this formula. Speed of sound equal the K is a constant times temperature we are going to see. Okay, but temperature must be in Kelvin scale. So in order to convert Celsius scale to Kelvin scale, we're going to add Celsius scale to the 273 Kelvin. Okay, so for example, there is a question over here. At 25 Celsius, the speed of sound through air may be calculated using this equation. Okay, speed of sound equal square root 400 times temperature. So in order to do this, you have to convert this 25 Celsius into Kelvin. How are we going to do it? 25 Celsius into Kelvin. So we are going to use this equation. 25 Celsius plus 273. This equation will give us in Kelvin scale, temperature in Kelvin scale. Okay, it is going to be 298 Kelvin. So now let's put what we have in this formula. So 400 times 298 square root. You have to multiply these two. When you multiply these two, and when you take out from the square root, you're gonna find the speed of sound at 25 Celsius, 345.2 meters per second. At 0 Celsius, the speed of sound is around what? You can do it. Okay, so you can multiply here 400 times 273. Okay, 400 times 273, and then you're going to put that inside of the square root. 400 times 273. When you get the square root of it, you are going to get 330 meters per second. Okay, so as you see, at 0 Celsius is 330 meters per second, but when temperature rises to 25 Celsius, the speed also rises to 345.2 meters per second. Okay, so that means whenever temperature increases, the speed of the sound will increase as well. Okay, this is important. So how do we describe sound waves? So what is the difference between louder and quieter sound? The difference is the sound waves are longitudinal mechanical waves. We can use an oscilloscope and microphone to help see sound waves. Okay, so and also what is the purpose of an oscilloscope? An oscilloscope produces a trace on the screen that varies depending on the sound entering the microphone. Okay, it is essentially a trace of displacement of the particles against time. Using an oscilloscope, we can see the effect of the change in volume and pitch. Pitch means the sound high or low. Okay, this is called the sound pitch, the volume and the pitch. So in order to determine it, we are going to talk about loudness. So the loudness of sound depends on the amplitude of the sound wave. Okay, it depends on the amplitude of the sound wave. What does this mean? It means the greater the amplitude, the louder the sound. What is an amplitude? Amplitude here, for example. Remember remember this one? This part called amplitude. Okay, from equilibrium position to the top of the wave, it's called amplitude. So for example, here you can see when you compare these two sound waves, you're going to see that this is going to be louder. Why? Because the amplitude here is greater than amplitude here. So you can say that the sound on the right is higher than the sound on the left. So for whisper, for example, it is 10 decibels. For the rustling wind, it's 17. For shouting, is 70. When you guys shout, you're gonna have around 70 decibels sound like amplitude. And for loud music is 100, and for jet engine is 120. So 120 is very high. You can get like what do you call it? Deaf when you hear, when you stay too much in the jet engine. That's why people who work like at the airport, they have like headphones, right? They use the headphones due to loud sound. Okay, they protect their ears. If they don't use it, they are gonna have problems. The sound may damage their ears. Okay, and the second one is the pitch. So the pitch of the sound depends on the frequency of the sound wave. Okay, the higher the frequency, the higher the pitch. Okay, so here, for example, here is lower pitch. As you see, the amplitude is very small. But when you come to over here, when there is frequency, more frequency, as you see, at the same time there are more there are more waves over here. So that means the frequency here is higher than here. That's why we are gonna see the higher pitch here than here. Okay, this part is going to be higher than this one. The third one is timbre quality. We call it. The quality of sound is called timbre. Quality does not mean that good or bad. Okay, it just refers to differences in the sound. It is not good or bad. Same note produces a different trace on the oscilloscope, for example. Let me show you here on the example. So for example, for whistle, you're gonna see this one on the oscilloscope. But on the other hand, for the trumpet, you're gonna see this. Okay? So this is the quality of the sound. It is not bad or good. We cannot say it's bad or good. Okay? This is because of the complex nature of the number of different vibrations produced by the instrument. Okay? Here for the whisper you use your breath. For the trumpet also use your breath, but here your mouse works. Here there is a device, it works. That's why the pitch, the timbre, the quality can change easily. Okay, the third one is echoes. Echoes, you guys already know about echo. When you shout, for example, in an empty room, you're going to hear your sound back. There is going to be a reflection of the sound. We call this echo. The reflection of the sound is called an echo. So if the sound produced in an enclosed space, it may produce a number of echoes. Okay, it can be more than one. It sounds like the sound is building up, then slowly decaying away. Okay, you're gonna hear the sound first, and then after some time, your sound is going to decay and it's not going to be here anymore. This is called reverberation. Okay, reverberation. If you hear more than one echo, and you're gonna see that echo is, you're gonna hear that echo is going to fade away in time. So this phenomenon called reverberation. Okay. What about the intensity of sound waves? The intensity of sound waves defined as energy received by the each square meter per second. Energy received each square meter per second is called the intensity of sound. A higher intensity would mean like more energy per second falling on each square meter. Okay. If you hear sound more, that means the intensity of sound is more. So the SI unit of sound intensity is watt per meter square. Watt per meter square. Power over area. Okay, power over area give us intensity of the sound. Power over area. So intensity is lower as the energy per second square gets lower. Okay, if the energy is lower, that means the intensity of the sound will be lower as well. So in all cases, the intensity of a wave can be determined using the equation below. Here we have equation, power of the area. Okay, if we can find it, since this is a three-dimension object, we can find the area by using 4 pi r square. Okay, 4 pi r square, we can use it and find the area of an object. So then the formula will be the power over 4 pi r square. That is going to give us intensity of the sound. Okay, so there is an example. Let's do an example and finish. After this, we're gonna have an example and we're going to finish our lesson here. Okay, before the example, let's define what does this mean. Okay, so from this equation we can see that if the wave travels twice as far, then the intensity falls to a quarter of its value. Okay, so 3 times, that means it is going to be 9. Okay, if it's 5 times, it's going to be 25. If it's 6 times, it's going to be 36 times. Okay, because of the here 4 pi r square. Okay. So there, let's go to an example over here. So a speaker has a power output of 250 watts. Determine the intensity of the sound 1.5 meter from the speaker. So let's do it. We have formula power over 4 pi r square, right? So our power is 250. The pi we are going to take 3.40, and the our radius is 1.5. Okay, we're going to take the 1.5 square. When we do this, we are going to get the intensity of the sound 35.3 watt per meter square. Okay, this is going to be intensity of the sound. As you see over here in the graph, how intensity change distance from with varies with the distance. When distance gets larger, the intensity gets lower, as you see. Okay, when distance gets like lower, the intensity gets higher. For example, a friend of you when shouts next to you, you're gonna hear more sound than when a friend of you shout at you at 6-10 meter away. Okay, this is called intensity of the sound, and this is the end of the this chapter.